Our final talk of this morning's session is given by Joachim Kock from the University of Copenhagen, and he's speaking on the universal property of the decomposition space of quasisymmetric functions.
Thanks. And I want to start by thanking the organizers for all the work they put into this conference. So far it has been really great. So the universal property of the decomposition space of quasisymmetric functions. So this is part of a larger program whose goal is to categorify algebraic combinatorics, and there's a lot of definitions I would have to make. Here's a little vocabulary. I hope to do most of it, but in case I don't, then at least it's on this hidden blackboard. But I think I should start with quasi-symmetric functions, and then I will come to the more categorical things in a minute. So the ring of quasi-symmetric functions is a subring of the power series ring in countably many ordered indeterminates, but they should be of bounded degree, and then they should be shift invariant. So what does it mean? It means that if I have a monomial x7 to the third x9, then I also need to have, like, for example, x1 to the third x2, because there's a shift of the variables involved where I sent 1 to 7 and 2 to 9, and it's a monotone shift. So you can see that there will be a huge number of monomials in a quasi-symmetric functions, and in fact you can write down the following basis. So let me write down the quasi-symmetric function M347 just as an example. So since there are three indices, I need to sum over all triples of natural numbers, and then I take the first variable to the power 3, and the second variable to the power 4, and the third variable to the power 7. So this is a huge infinite sum. So I need to do this in order to satisfy shift invariance. So this is called the monomial basis. So every quasi-symmetric function is a finite linear combination of these. So this is also a graded ring. Every indeterminate has degree 1. And I need to mention also the special zeta function that it has. So this goes from, it just means linear functional, and this one, it takes m n to 1, it takes m of the empty, so that's just the algebra unit, to 1, and then it takes others to 0. So that's the special zeta function on this algebra. In terms of the monomial basis, the co-multiplication, it's a half algebra, I should say. So the co-multiplication is deconcatenation. That just means that I split these words in all possible ways. And the multiplication in this basis is the quasi-shuffle, also called the overlapping shuffle product. So instead of just shuffling everything, I'm also allowed to join things from here into here to, and I'm not going to use it, so I don't want to spend time on that. Okay, quasisymmetric functions come up a lot in many places, and the reason is the following theorem, which is due to Marcel Aguiar and Marcel Bergeron and Frank Sotal, 2004. It says that the ring of quasi-symmetric functions with its special theta function is terminal in, now I write a category, graded coalgebras with a theta function. And again, theta function just means a linear functional. But it should, however, agree with the co-units in degree 0. So graded coalgebras with a theta function. Okay, so in this program we want to take things from algebraic combinatorics and lift it to the categorical level, and most of the time we use simplicial methods. So maybe I should just put up here algebraic combinatorics, the simplicial methods, and I should put my co-authors from, we started this program 10 years ago, and I talked about it at CT14, so you have to find your note from CT14. I'm really happy to see so many new faces, so I don't assume you have been to this talk. So, first of all, I think I prefer to erase here. So I want to present a categorified version of this theorem. So first I need to go all the way up to vector spaces, and linear maps are modeled by slice categories and spans. So it's easy to see when you have a span. It looks like a matrix and you multiply by callbacks and so on. But it also defines a functor from slices, namely by pullback along P and lower streak along Q. And this preserves all limits, colimits. So this is the main idea, that we want to do algebra in these slices. So, coalgebras. Okay, I actually had a plan. I better follow the plan. The plan is first to write down the theorem, because then I'm safe, and then I just define as many things as possible. So, theorem with Philip Packard, myself, and Jan Steinhorn. Given a graded decomposition space X with a theta function theta, there is a unique graded span So here we have x. To say that x is graded means that there's a conservative simplicial map down to Bn, the class map space of the natural numbers. It's on the list, I will explain it. There's a decomposition space Q, whose incidence coalgebra is quasisymmetric functions, and it's also graded. And the theorem says that there's a unique span from X to Q, and this is Aikio on the left leg and Kulf on the right leg, such that the zeta function here induces the zeta function here. Okay, so that was the theorem. Some of the things are already explained here, but I will do it in more detail now. So the point is that these spans model coalgebra homomorphisms. And it's clear that if you have such a span, you get a coalgebra homomorphism, as I will explain. It was suggested by André Fayal that conversely all coalgebra homomorphisms coming in this setting should be of this form. And it has been proved recently by Josef Gödige, but it's not out yet. So now this correspondence between coalgebra homomorphisms and Aikio spans should be safe.
So what is that class on the left again? The left class?
Sorry, what's that?
It's some kind of map and then a cult map. What is that?
Aikio. I will do that now.
You make it yourself?
Okay, so now I will start doing all the things that I need to say to make sense of this. I'm sorry for doing it a little bit backwards, but I'm afraid I don't have time for all the definitions, so at least now we have the theorem. So, let's step back to a small category C and look at its nerve. Then, since Rota and Leroux, you can define a coalgebra on the vector space spanned by the arrows. So now I define the co-multiplication of this coalgebra. It takes an arrow F and returns the set of all decompositions of F into two steps, and then you just put these two arrows in the two factors of the co-multiplication. Now, I already wrote this simplicially, and the point is that this formula can be written completely simplicially by summing over all two simplices such that the long edge is F, and then you return the two short edges. So you can see that this assignment makes sense for any simplicial object, but the question is, will it be co-associative? And the notion of decomposition space, which is due to Galvis, Kock, and Tox, is, well, X is a simplicial space with decomposition if this co-multiplication is co-associative. And when I say co-associative, I mean up to coherent homotopy co-associative. And S is the infinity category of spaces, or infinity groupoids. So that's of course not a definition. To make a definition, I think I can erase the original theorem now. The definition is a little bit technical and depends on some final features of delta. So the category, the simplex category, has a factorization system of active maps and inert maps. And we already saw that in John Burke's talk. He pictured them wavy. We usually do like this. So these are endpoint preserving. And these are distance preserving. So if I just look at the maps from 2 to 1, then there's 3 cophase maps here. D0 omits 0, D1 omits D1, and D2 omits 2. So we see that this is distance preserving, this is endpoint preserving, and this is distance preserving again. And it's not a coincidence that the active map appears here in the summation, and the two inert maps appear in the actual returns. So this whole formula is given by the following span. Well, here you have D1, and here you have D0, D2, D0. So you start with something here, you pull back here to get the fiber over F, and then you just compose. So this is how these co-multiplications appear from simplicial objects. And now, what does it mean to be a decomposition space? It means that all active inert equations or simplicial identities are pullbacks. So let me write an example of such a thing. So if I put D0 here, then I have to put D1 and D2 here. So D0 there inert. And these are active. So we have to demand this to be a pullback. This is just a simplicial identity, but we furthermore demand it to be a pullback. And it comes up when you try to just write out the co-associativity here. You compose spans and you see that this is what you need. Now, this is only the first of these active inert equations. The reason you need them all is because we want this to be co-associative in a coherent way. So this is just the first of an infinite series of squares that you demand to be pullbacks. So everything here is based on pullbacks, and maybe I should put it in this list. So why are the pullbacks all over the place? That's because pullbacks are just families of bijections. If you look at the fibers of a pullback, you will get bijections. So that's why there's a lot of combinatorics that can be expressed by pullbacks in the end. And this is one of them. Okay, so now we have a decomposition space and co-algebras. And that doesn't appear so much in the theorem because we already assumed this to be decomposition. And this, I will tell you what it is. But the co-algebra homomorphisms, that's where we see Aikio and Kulf. So I have to explain that now. I keep the span down here. So if we have a simplicial map, then we can write down the span, define the co-multiplication of y, and the span defining the co-multiplication of x, and we have the components of the simplicial map. And now we would like it to be a co-algebra homomorphism. And if we want to go forward, then it means that doing this would be the same as this. And the crucial part is pull-push should be pull-push. Sorry, push-pull. So this is why you need a pullback so that you can apply big Chevalier. This is if you want to go forward. If you want to go backwards, we should start here and go this way. And now there will be a pull-pull, that's fine. But here there will be a push-pull, should be a pull. No, what am I doing? Sorry, backwards, I should start here. And then there will be pull-pull, no problem. But here there will be a push-pull. So then I need to put the pullback condition here. And this leads to the following two definitions. So F is Kulf when Cartesian on active maps. So QULF stands for conservative and unique lifting of factorizations. So this goes back to Louvier. Conservative means basically co-unital, and ULF means basically co-multiplicative. And if you write it out in pullbacks, it means precisely, or it will imply that this square is a pullback. This is an example because these are active maps. So that's QULF, and the other one is IKEO. IKEO stands for inner Kahn and equivalence on objects. So it basically says this one. So if we look at this square and ask it to be a pullback, it says basically that you can reconstruct a 2-simplex if you know it's 2 principal edges and you know it's 2-simplex downstairs. But this should be demanded for all n, not just 2. And in particular, it should be demanded for n equal to 0. In that case, it says that there's only 0 many factors here. So you see that it says that it's an equivalence on objects.
Sure.
Okay, so QULF you can go forward and you get a coalgebra homomorphism. IKEO you can go backwards and you get a coalgebra homomorphism. So this is why we want IKEO QULF spans to model coalgebra homomorphisms.
Josh, 4 minutes.
Yes. Okay, and now to finish, I'll just give you a very short idea of how this is proved. Because in a sense it's very formal, but there are many details that I cannot tell you. So up there you can see that grading is a conservative map to the classifying space of the natural numbers. So the input to this theorem is a conservative map here. And the idea is we just hit it with a functor that produces the rest of this diagram. And this functor is, well, I hope it will work out. So the inert maps form a subcategory of the whole thing, and the inclusion is called J. Then it's a theorem that Philip Hack talked about last year, that for any delta inert diagram, this one is actually a decomposition space. So whatever you put in as delta inert pre-sheaf, you get a decomposition space out. And the other thing is that whatever map of such diagrams you put in, this will be QULF. Okay, that takes some work, but now the point is that Q, I will finally define the decomposition space that gives quasi-symmetric functions. It is just J over 3 of the non-degenerate synthesis of the classifying space of the natural numbers. So when you take only the non-degenerate synthesis, it's no longer a delta pre-sheaf, but it's still a delta inert pre-sheaf. So you can apply this one to it and get something, and in this case you get Q. You also get a grading, and that grading is actually the co-unit of a comonad. And the comonad is, this assignment is a comonad, and this is actually the co-unit. And now there's some things to check. For example, that if you, I already said that if you apply the 20 map, you get a QULF map. So here I have to put this one. And then I get the QULF part of the span. But there's one thing you need to check, namely that the co-unit is IKEO on decomposition spaces. So we also get this map, and that will be IKEO. So now I have told you what the map is. I have not mentioned at all what uniqueness is, but that comes from the functional, the zeta function. I don't want to go into that. So this is how it ends up, at least constructing the span. And I think I should stop here.
Questions? Yes.
It's really cool how slick it worked in the end there. For IKEO, do you really need all the inner con, or do you just need the maps and the products over the spine of the...
It's equivalent because there's also the condition in degree 0 that I erased. So since y and x have the same zero simplices, whether you take a fiber product over x or a fiber product over y is the same thing. So it's equivalent to what we are saying.
In all higher degrees too, not just 2?
Yes.
Okay,
So you can write the condition with fiber products instead of products, but then you need to put degree 0 separately.
Thank you.
Other questions? Yes, Richard.
So, consider a hypothetical person who's slightly allergic to simplicial sets.
So,
Consider a hypothetical person who's a bit allergic to simplicial sets.
There are no such people.
yes.
So, for that person, could you restrict X to be a discrete decomposition space, and then construct Q as a sort of decomposition category or something like that, or groupoid,
Yes.
and then get a version of this result that still works?
Yes. So I could work with simplicial sets instead of simplicial spaces. I should probably take a decomposition space as input anyway, because the point is, Kulf over a category might not be a category, it's always a decomposition space. So decomposition spaces and Kulf maps, they work well together. So I would not stick in the case of categories.
That sounds like a no.
No.
Other
Or
questions?
maybe yes, but I wouldn't do it.
Anybody else? Let's thank our speaker again.